Okay, good afternoon. Can you hear me? Cool.
Yes.
Excellent. Thank you. Okay. So today I want to start out with some more information about the lab that's due on Friday because I had several students asking about how to get started. And I realized the reason for this is because even though I introduced the lab in the last lecture, and we have we obviously have the lab sheet as well, but neither one of those things tell you what to expect when you open up the skeleton, one of the skeletons that we give you. So I just want to give you a quick tour of that so you can get your bearings in case you might not have looked at it yet, or if you did, you might be confused. So let me share my screen. Share. Okay, so you should see a Linux desktop there, and I've got Chromium pulled up, and I've got the Dropbox for the course pulled up. Hopefully you can see that. And so first thing I'm going to do here is download the skeleton. And so I will choose the Python language, template rather, not skeleton. I'm going to choose the Python language template. This is not to indicate that we want you to use Python or we prefer it. You can use either language. So I'm going to click that and just hit save that. And that will be downloaded into my downloads folder. I'm going to create a lab 1 directory here and go to the lab 1, and then I'm going to move that downloaded file out of there to here, and then untar it. And then I get another directory created called Lab 2021 Spring Parallel. And here we are. So this has a code directory where you put your code, and then there's a grade script called grade.sh. So the idea with this is that you run the script and it's going to tell you essentially what grade you should receive. And then if you go into the test cases directory, you'll see that there are 21 test cases in there. For each one of the test cases, for example, if we look at test case 0, you'll see that there is an input, which is the trace file that I described in lecture on Monday. And then there's also an expected output. So the expected output from this is 23 and 93. These are the two hexadecimal values that correspond to the 8 bits of the data bits that are sampled on the rising clock edge. And there's 2 values there because there's only 2 clock edges, which you can confirm by looking at this first column, and you see that there's only, as you read from top to bottom, because time in this case is flowing from top to bottom, you see that the clock only transitions from 0 to 1, meaning a rising edge. It does it once here and it does it once here, but so there's only 2. So because there's 2 0 to 1 transitions, we have 2 corresponding values. And 23 would be the value that basically you would see on these bits, but of course you read them backwards because they're ordered backwards. They're ordered from least significant to most significant. So you can see that if you start from the right and work your way to the left, you have 0010, which is 2, and 0011, which is 3, and that matches up to the 23. So that's basically the input and the expected output, and the grading script essentially just compares the output of your program to the output in this test case. If you look at other test cases, like test case, for example, 19 or 20, say, this one is significantly longer. You can tell right away because if you do a directory listing, sorry, 20? Yeah, their input, if we look at the output of this guy, there's a lot more values here. 128 to be exact. So those are the test cases. Now the grading script is what you run the grading script from the top level directory, and that's also the script that you would run with the --pack option in order to create a submission package for your solution. Now, the first time, if you're doing what I'm doing and running this on your local machine, you'll get an error when you run the grade script, or you might get an error saying that you don't have the virtual env package, or can't find the virtual env command in the path. And that's an easy solution to install that. You can just type sudo -apt-get install virtual env and hit enter, and put in your password, your root password, and then, or your user password rather, and then that will download not only virtual env, but it also will bring down Python 3 as well, because that is a virtual env depends on Python. And I think that's the only thing you'll need, although as I mentioned in the last lecture, if you do this, make sure that everything works on the Linux lab machines in the department, because that's the environment we'll be grading on. And so, for example, if you have a different version of the Ubuntu, or if you have a different Linux distribution, from the one in the lab, you're going to want to make sure that your solution runs in the lab and that it comes out. Basically, yeah, that's it. And then the first time I run this, I will get another error message. I'm going to run grade.sh, and it says, error, could not determine user ID, please create the file, blah, 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 blah. This is something that was described in the lab sheet. So the easy way to fix this is just echo your username and then redirect that output to the file, which you can just copy and paste, and then run the grade script again, and then it will run. So in this case, it says that basically it says there's a failure, so it's going to try to run all 21 test cases, but if it fails on any one of those, it bails out of the entire process. And so in this case, it failed on the first test case, so it just stopped with that one. It just assumes that if one fails, the rest of them will fail. But one of the confusing parts about this output is that I mentioned that the grading script is comparing the expected output to the actual output, and it does that using the diff command in Linux. And the diff command has got to be the command that has the most confusing output imaginable. It gives you, basically, this is the output that you're seeing from the diff command. So you got some @ signs, which who knows what the hell that's all about. Unclear what's going on. But basically, the main takeaway here is that you've got these plus signs here, which means that there are lines in the expected solution that aren't in the actual solution. And if you had lines in the actual solution that aren't in the expected solution, then those would be preceded by a minus sign. So don't get too intimidated by this crazy @ symbols and +1, +2, who knows what the heck that is. Just basically understand that this is an accounting of the differences in the files, and it does it by line, not by character. So you might have two lines that are identical except for one character, and then diff will freak out and say the whole line is bogus. So just be aware of that's what's happening here. The other thing you have to be aware of is whenever you print something to the console in Linux, and somehow this was also carried over to other operating systems as well. But Linux, that's a good question. Adam wants to know if it can be done on a Mac. I assume so, since it's BSD based. But Charles would have a better answer. Sorry, I lost my train of thought. Oh, yes. When you print something to the console, there are two output streams. One is called standard out, and one is called standard error. And the grading script, now, if you just print something in the console, as a user who's just looking at the console output, you don't know the difference. There's no way to tell what's being printed to standard out and to standard error, because they both go to the console. But if you're redirecting the output of a program to another program, or even to different files, then there's this distinction. And the way that we use this in the grading script is that whenever you print anything to the log, it goes to standard error, and anything you print to standard out is what the grading script is going to see. So in this case, you'll notice that under actual, there's nothing, meaning that the program doesn't print anything. But if you go into the logs directory for the first test case, since that's the only one that ran, you can actually see that there's a run.error and run.out. So if you look at run.out, it's a 0-byte file. Obviously, there's nothing in there because nothing was printed. But if you look at run.error, this is the stuff that was printed to standard error. And so there's some information in here, including essentially a part of the whole trace, just the least significant 4 bits for some reason, not the whole thing. So there's this weird subset of the trace file being printed in here. And you might say, well, wait a second, I didn't print a darn thing. I didn't print anything. I didn't even put any code in yet. This is an empty project. Why is there stuff here? Well, these messages were printed to standard error. They were part of the template. So this was kind of we gave you some code that's already printing something. So even if you just run the raw template, you're going to have some output that's not seen by the grading script because nothing was printed to standard out. But you do have some stuff that was printed to standard error. And of course, this standard error is being used here basically for debugging and to provide a way to print stuff without the grading script seeing it. The problem, of course, is that when you run grade, you don't necessarily see anything that's printed until you drill down into the logs file and take a look at these files. So this is kind of an indirect way of seeing the output of your program. It's not direct in the sense of every other programming course you've ever taken where you run something and you immediately see the output. The output is actually deferred and kind of redirected into this log directory, unless you run the Python script by itself, which is possible, but not the way that it's intended to be run inside this environment. Okay, so if we go back to the root directory and go to the code directory and we open up main.py, this is the program that we provide. Now, this is, I think, what's confusing a lot of you guys that have looked at this, because there's a lot of basically crap in here that's sort of unexplainable. There's a bunch of stuff being set. We don't know why. But once you get down to this line of code, line 30, you can start to see the actual behavior of the program. This is when we instantiate the waves object, and I talked about this in the last lecture. So the waves object is the main data structure that's intended to store the trace that we're reading and interpreting. So we have this raw signal trace, and our job is to basically interpret that trace. So basically, we want to act like a protocol decoder, except in this case, we're not actually decoding a protocol. We're just doing a very simple, looking for clock edges and grabbing the data. So we're basically filtering the trace and doing a taking bits and assembling them into words. That's essentially the type of decoding that we're doing. So so you'll notice that we instantiate the waves. Now, another reason why this might be confusing to you is because in my lecture on Monday, I implied that you were supposed to do this. But in fact, you don't, because it's already done. So the waves is already instantiated, and the load text, which is another method in the waves class that I described, is actually already in here. And this is what's going to read the trace file from the standard input, as opposed to reading it directly from the file. It's actually read. The wave is not read from a file. It's blasted into this thing through standard in, which is fine, because if for all practical purposes, you're treating the standard in like a file here and you're loading it. Okay, and then here is a sys standard error write. This is the messages that we read in the log under standard error. So these are log messages. I mentioned to you in the C skeleton, there's actually a log macro that we provide, but in the Python, we're just like, nah, just do it yourself. Write the standard error. And then in this case, we have another message that writes out the kind of a debugging message, sanity check. This prints out the signals. This is also intended to show you kind of how to access that data structure. Okay, so then finally we get to a loop. Okay, so there's 2 loops in this thing. There's a while true here, and there's another while true here. Now, you might be confused, and you might be thinking, why are there 2 loops? We're supposed to do 1 loop. We're supposed to look for clock edges and grab the data. That would be 1 loop, and you would be right, but we have 2 loops. And the idea here is that the 2 loops do 2 different things, but they're intended to kind of show you how to use the library that we provided. So the first loop, first of all, it initializes this variable t to 0, and then it calls next edge. Next edge is a method in the waves object, and this is something I also mentioned last time. This will return a tuple that will return the next it'll return what the time is of the rising edge of the clock after the after parameter, right? So we start out as 0, so we pass 0 in as the after parameter, which will find the first edge, and then after we repeat this, after we loop again, the t, which is, again, it's being used as an input and an output for this line of code, the t is then going to, on the second time we call next edge, t is going to be the location of the first edge. So since we're starting at the location of the first edge, this will return the time of the second edge. Now this time is not in cycles, this time is actually in seconds. Okay, so this will be, a floating point number, and then the OK is going to be true or false. Now the OK is important that you have that, because this is the way basically you end this loop. If OK returns false, that means there's no more edges, or there's no edges after the time indicated in the after parameter. And that's what this if statement does. It says if not OK, meaning that there's no more edges, then break, and that will break out of the infinite loop. If that is not the case, then you print the rising edge time, and then you're basically you're done with that loop. The second loop then, the second loop goes back and it actually grabs the signals at specific times, but it's not looking for edges, so it's actually going to grab every time, basically. So this kind of just dumps out, kind of regurgitates the trace file, but in this case it's only doing it for S0 through S3. What it's not doing, though, is it's not putting those bits together into a word. It's just printing those bits out as bits. So your job is to basically just go to the first for loop and then add just basically one line of code after this if statement. So it's important that you put this after the if statement, because you only want to do this if you haven't, if there's another rising edge, if you found a rising edge. So if you add a line of code after this if statement, this will execute whenever you find a rising edge, and then you need to just simply use the W signal at. So for example, you can copy and paste this line, right? And this will give you the S0 at t, and t is the basically the t is the same variable that we're using here, and that would be the time that was indicated, the time in which the clock edge occurred, and that's also, of course, when you want to pull out the data wires. So then you could just grab that, and then of course if you OR that together with signal 1 and then shift that by 1 bit to the left, that would allow you to start concatenating these values up, these binary values into a single value, and then you could then assign this. I only did it for the first 2 bits. You would have to expand this for all 8 bits, but you would collect these signals and then assign them to some kind of to a variable that you create, a new variable, and then of course you can just print that out to standard out, and that's all you need. Now, one thing I want to mention here, and probably the trickiest part of this lab, is that despite all of the intelligence that's been built into this grading system, it's deliberately not looking, it's deliberately very strict about the output format. So for example, you're going to print hexadecimal values. So you print 2 hexadecimal digits for every rising clock edge, where that 2 hexadecimal digits represent the 8-bit value of the data bits. But you better make sure the capitalization is right. So don't use uppercase A through F in the hexadecimal. You got to use lowercase, and you got to also make sure that you pad the values with leading zeros in the cases where the value is between 0 and F. So, part of the tricky part here is that, we sort of give you a false sense of security. We have all this intelligence in the grading system, but it's not quite smart enough to realize that capital A and lowercase a are the same thing. And that was intentional. That was kind of, so you can figure out, basically, so you can, read instructions and follow the instructions. And as Charles notes there, he's actually, if you look at the lab sheet, if you read carefully, you'll see that, in fact, you can literally just copy the line of code, and it'll show you how to do the formatting. And that's a little tricky in Python. There's multiple ways you can format. There's the % operator, there's the dot format method on string objects, and blah 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 blah. And of course in C there's the printf, and then there's I don't know if you can use C out, if you can use C++ stuff, but there's different ways to do the formatting. But we give you at least one way to do that in the lab sheet. But just be aware that if you do it yourself and you don't read the lab sheet, you'll probably run into the same error I did, which is error, A doesn't equal A, you know, that sort of thing. So be aware of that. You got to make sure you're careful with your output formatting. Okay, so I'll just make you aware of that. I don't want to give too much away here, but if you have any other questions about this, definitely, you know, let us know. Feel free to let us know. Don't hesitate. And by the way, when you do this, you know, because this secondary loop is printing to standard error, it doesn't affect the grading script at all. So you can leave that second loop in there. You don't even have to take it out, or you can even add more standard error prints if you want, because you know, anything you print to standard error will be ignored, and it's basically useful for debugging purposes, which is useful because, of course, you can't run this through a debugger when you're using our framework either. So you can print anything out here to standard error you want. You can leave the second loop in. It's not a problem. So that's another quick tutorial. Remember that this is due on Friday, and if you have any questions, you know, feel free to ask them now, or if you think of any later, you can email us. And just I want to remind you again, make sure that this runs on the lab machines before you finish it up, before you submit it, and if you need help connecting those lab machines, let us know. Also, I checked. Remember that. Well, so decimal. So there's no decimal here. It's you're reading bits, and yeah, I mean, I think you can use anything built into Python. I'm not sure if you can add packages. I don't think that's, Charles will answer that. I'm not sure if that's fair. But anyway, yeah, the intention, I think, was for you to use some bit twiddling, as I taught in the first lecture, to form these values. But you know, of course, Python has a lot of tools that you can use to simplify things. Okay, one other thing too, I want to remind you about the quiz that's due today at 6 o'clock. If you didn't do it, I think all of you did it. Grades were very good. We had, I think, 83 attempts. And I checked the grades, they look good. But just in case you forgot to take the quiz on Blackboard, sorry, not Blackboard, on Dropbox, make sure you do that by 6. And you know, 6 will, you know, you should have some time after class to do it. So hopefully you don't bail out of the class to do it. Okay, now I'm going to switch over to some slides. Okay. Alrighty. So you should see my slides. Okay, so last time we take the grade from the last attempt, not the highest grade. So yeah, just be aware of that. That's a good question. I thought when you recorded it did save the chats, but I see that it, you know, it doesn't. I don't know about that one. Charles might know. You can copy and paste the chats. Yeah, Charles just said Control A, Control C. I don't think there's an export or any kind of fancy way or formatted way to do that. Oh yeah, maybe if you play the recording in Blackboard, it'll show you the chats. The way that I export the recordings as an MP4 file, and then I upload it to Dropbox. And that's the way I'm used to looking at the recordings. But if you view the recording on Blackboard, then it might show you the chats, according to Alfred. So good. All right. Yeah, that's very cool. I like that feature. I thought it recorded the chats. Okay. All right. Let's see. So last time, let's see. Let's close that. Let's zoom in a little here. Okay. All right. So yeah, the reason I don't maximize this window is because I want to be able to see your chat. So sorry about that. So last time we kind of tried to tie up SPI. And I'm just going to review that pretty quickly. I don't want to spend too much time, but if you have any questions as I go, let me know in chat. Okay, so we talked about how the SPI SPI transactions. So I mentioned that SPI, the protocol itself, doesn't define a way to do programmed I/O. It's really just, it does exchanges. You know, I send you a byte, you send me a byte, and that's essentially how it works. So obviously we want to be able to do programmed I/O. Programmed I/O is kind of the fundamental way that CPUs talk to hardware. Programmed I/O is, you know, when you load or store, or you read or write to an address. And so SPI, you can do that over top of SPI, but the way that you do that is going to be specific to each peripheral. So in this lecture, I'm showing you some examples of how to do programmed I/O over top of SPI, but this is not to mean, we're not trying to say that this is how every peripheral would do it, because this is, most of these screenshots and information are actually coming from a specific device that we used last spring, this accelerometer, and how it worked, although I think it's representative of a lot of peripherals, but this is just, you know, one way to do it. And so this example I'm showing on the screen is not in the slide set on Dropbox. I need to update it. I just added this. This is a new example. So in the following SPI transaction, assume the transaction address is stored in the least significant 5 bits, and the read-write flag is stored in the most significant bit of the first byte transmitted from master to slave. What is the transaction? So in this case, we have cpull is 1 and cfa is 0, which means that the data should be read on the falling edge of the clock. So cpull is, yeah, control flags I think are the main thing. Charles, yeah, that's what I was mainly concerned with, is the control flags. And so so control flag being this read-write flag is what I'm talking about specifically. So the read-write flag is stored in the most significant bit of the first byte transmitted. Okay, so first thing you got to figure out here is, where do we get the bits out of this timing diagram? Where do I sample the bits? And so as you can probably, you know, you might be thinking, well, this is what the lab is all about, right? The lab, the whole point of the lab is to be able to, you know, look for times to read bits, right? Because we give you a trace file with a whole bunch of data in it, but we only expect you to read the bits at certain points in time, as indicated by the rising clock edge. So when you look at this timing diagram, you're really doing the same thing that you're doing in lab 1, except in the case of lab 1, you're writing a program, and here you got to do it kind of by hand. So because cpull is 1, that means the clock is normally 1, and the first time it drops, it's going to have a falling edge. And the first time, because cfa is 0, then you can expect the data to be stable on that first falling edge. So, but if cfa was 1, you'd have to look at the second falling edge, or actually in this case it would be the rising edge. So in this case, because cfa is 0, I'm going to look at the value of MOSI and MISO. I'm going to look at the value corresponding to the falling edges. And again, if cfa were 1, then all of this would be pushed to the right. All of these samples would be pushed to the right by 1/2 clock cycle, because I would have to phase shift 1 cycle to the right. But cfa is 0, cpull is 1, so I'm looking at the falling edge of the clock. So I've put these, I've shown this a little differently this time. Now the arrows are pointing at the data that's relevant, and the arrows are aligned on the falling edge of the clock. And you might say, okay, why are these arrows high and these arrows low? Well, because the first bit is a 0, and 0 means I'm reading. And so I have to do 2 SPI exchanges, the first being the address and flags, the second being the data. But because it's a read, basically the master is going to forfeit its second byte, and the slave is going to forfeit its first byte. So basically the important bits here are the data sent from the master during the first byte and the data sent by the slave during the second byte. And that's why I drew the arrows like that. So the address would be the least significant 5 bits of the first transaction. So that would be reading from least significant to most significant would be 11010, which if I now reverse that, is going to be 0 and 8 plus 3, 11B, 0B in hex is the address. And then you'll notice in the second byte, the master just kind of pieces out, and the slave kind of takes over, and the slave is going to send 111000011 back to the master, and the bit ordering here is most significant bit. Oh, I'm sorry. So I was wrong about the address. Sorry, scratch that. This is most significant bit first, so I would read it from left to right, the address. So the address would in fact be It looks like 1. Oh no, I had it right. I was reading it right. Sorry. Yeah. No, never mind. Scratch that. It's it would be 0B, right? 0 and B, right? 1 0 1 1. Yeah. Sorry. So I'm reading from left to right there. Now SPI could be either way though, so you have to pay attention to the bit ordering. Okay, and then I mentioned last time there's this idea of multiple reads too. So SPI supports, essentially this would be kind of like streaming data. So in this case, I've got this MS flag. Now you might say, why didn't you have that MS flag in your previous example? Well, that's because the previous example was, a protocol I made up. This one has, this protocol has the MS flag being the second bit sent from the master during the first byte in the first exchange. And in this case, that would indicate whether you're going to do multiple reads or writes. And so in this case, you can see that this is obviously a read, because you can see that the slave kind of starts sending data starting with the second byte, and there's also a third byte, so there would be 8 times 3, 24 total bits in this transaction. And so here's another example of that. I think I showed this last time. But again, you look at MISO and MOSI, and the header is, I call it the header, but it's basically the first byte, and then the bytes that are transacted come after that, and they're all part of this big transaction as indicated by the slave select. And then here's a multiple write, works the same way, except in this case, there's no data that comes back from the slave device. Okay, so then I got into this idea of shared connection. So SPI allows one master, but potentially multiple slaves. That's important when you have more than one when you have more peripherals than SPI channels on your device. And you might say, well, why are SPI channels so expensive? I mean, why not? Oh, I mean, they have a cost. There's 4 pins for each channel, so. Obviously, your chip is going to be limited on the number of channels. So there's 2 ways that you can do multiple slaves. You can connect. You can basically have all the slaves read the clock and the MOSI from the master, but then you can give them separate slave selects. So this way, the slave would know if it's being addressed by the master by its individual slave select. Now this of course would require more than 4 wires, so you would require basically 3 plus n wires in this case, where n is the number of slaves. Then you can also do a daisy chain approach, which is a different way of doing it, where it still requires only 4 wires regardless of how many slaves you have. And in this case, you daisy chain the MOSI-MISO connection. So you have MOSI coming out of the master, goes into the slave, and then the slave will then take its MISO, and instead of connecting it back to the master, it'll send it to the next slave down the line, and then so on and so on. And eventually the last slave will send its MISO back to the master. This way, you only need 4 pins in total on the master, and all of these guys would still need to share the clock, and they would all share the slave select as well. The difference would be that it may take more cycles to cycle data all the way through this daisy chain. So that's the difference. Now with option 1, there's this other problem you run into, I mentioned, where if you're using option 1, all of the slaves are going to have to share the MISO. And that's a problem because you can only have one device drive a wire at a time. And the reason for that is because of this push-pull interface that they're using. Basically, when you have a slave drive MISO, it's either going to short MISO up to power, or it's going to short it down to ground. But if you had 2 devices that had different ideas of what it wanted to put on MISO, in other words, there was a conflict where one was trying to send a 0 and one was trying to send a 1, then you would end up with a pathway where you've got the MISO connected to the VDD on one chip and the ground on the other. So what would end up happening there is that current would flow from VDD down the pull-up transistor and then across the wire, the MISO wire, and then it would sync it down into the the ground of whatever device is trying to send a 0. And so I mentioned that, you know, this is essentially a short circuit. This probably wouldn't be devastating in terms of damage because these wires have resistance. So the longer these wires are, and not only the wires, but the solder joints between the chip and the circuit board, or the chip and the breadboard, you know, basically, as well as the chip and the package, the wire bonds between, or the bump bonds between the chip and the package. So there's a whole lot of resistance along this path, and hopefully a little bit later in the semester we're going to talk in detail about how these transmission lines work and how they're modeled. But basically, it probably wouldn't be a huge amount of current. But and this is an example where I just said, you know, if you assume that the on resistance of a transistor is 1 ohm, the pull-up transistor is 1 ohm, and the pull-down transistor is 1 ohm, you have 2 total ohms, and so that would give you 2.5 amps over 5 volts. But again, that's assuming that there's no resistance on the wire. So these are just example numbers. But the bigger problem here is that the voltage would be somewhere in between, you know, 1 and 0, and so these guys, you know, the master would then be confused because the master would be seeing 2.5 volts back from the meso, and it would be like, I don't know what to do with this. So you don't want that. So the way to solve that, and this is how some chips do it, is that they add these tri-state gates. So it allows them to electrically separate themselves from meso whenever they're not being used. And so that's a possibility as well. And like I said, some chips do that, some chips don't. You should also always read your data sheets. So another solution to this problem, though, is this idea of an open drain type interface as opposed to the push-pull. Now this is kind of neat because this is similar to how all logic used to work back in the days of NMOS logic, back before CMOS came out. So this is kind of 1970s technology, but it's still used for doing off-chip interconnects. So basically the idea is that if you eliminate the pull-up transistor entirely, so you just have a pull down, and then you connect the wire, the output, to VDD just through a resistor. In this case, I'm showing a 10 kilo ohm resistor. That's not necessarily what you'd use, but that's just an example. Now this is nice because it theoretically allows multiple chips to be able to drive one wire without having to worry about tri-stating the bus. So the way this works is that if nobody is sending if neither one of these chips is sending a 1 on the wire, in other words, I'm sorry, if both of these pull downs are off, I should say. Okay, so neither one of these chips is turning on its transistor. What'll end up happening is that the output voltage will go up. It'll basically be whatever the voltage divider is between the off transistors, which is about a mega ohm on the downside, and about 10 kilo ohm pull up on the upside. So that ends up giving you, if you work out the voltage divider, it'll give you a voltage of 4.9 volts. So you won't get the full, you'll still get a voltage drop over that pull-up transistor, but it'll be well within the acceptable noise margin, right? So you'll be up above the, whatever the minimal high voltage is for the logic. So basically the idea is that what that does is it makes the default value 1 on the wire. Now the problem with this is that, and it's not a big problem, but what that means is that, you know, you're going to have some leakage current, but the leakage current actually in this case, in this state, is not a big deal because of these 1 mega ohm resistances you have on all of these pull down transistors. Now the problem though is that the more devices that you put on this wire, the equivalent resistance, even when these guys are turned off, is obviously going to go down because you're going to have a bunch of parallel resistances of 1 mega ohm. And so the more devices you have connected to this wire, the more leakage current you're going to get. But as it is now, the leakage current is equivalent to the push-pull, which in this case should be about 10 microamps. So that's not a big deal. Now, if one of these guys on the bus though one of these devices on this wire decides that it wants to send a 0, so the default state is 1. If it wants to send a 0, then it just has to turn on one of these transistors to pull down the voltage down to 0. And so what that'll do is that'll start sinking current, through the pull-up resistor and then down through the pull-down transistor here. In this case, this will pull down about 0.5 milliamp. And then the voltage of this guy will be the voltage divider of basically 1/10,000 times 5 volts, which is very close to 0 volts. So that should get it down pretty close to to ground level. Which is good. Now the reason this is nice is because if, for example, one of the other chips on this bus has a collision, like there's a conflict. There's two devices now that want to pull down. Okay, well, what happens? Is this going to be devastating? Well, no, it will double the amount of current coming down. We'll still get 5 milliamp or 0.5 milliamp on either side, but it's not a big deal because we have this pull-up resistor. So we're not going to end up pulling a lot of current through here, and our voltage will still be down around 0. And typically, when this happens, the chips are also able to detect when this happens as well. They can detect when there's two devices that are simultaneously trying to drive a 0. Now the problem, though, of course, is that there's no way to detect if there's a conflict with 1, right? So if two chips are sharing this wire, they both want to send 1. Well, there's no way to detect that because 1 is the default state of the of the connection. But if there's more than one device that try to draw 0 or send 0, there are ways to detect that. And so this is how the next protocol that we're going to talk about, I2C, this is the way it works. I2C stands for inter-integrated circuit, which I think it's a really clever name. Because inter-integrated circuit is exactly what's happening. It's a chip-to-chip interconnect. I don't think anyone's ever used this for on-chip, inter-chip. This is between chips. So inter-integrated circuit, and it's like I2C. Where this, it's the 2 is an exponent, although sometimes I forget to superscript that and I just say I2C. I try to remember to superscript that too. But basically the idea is that there's only 2 wires now in this connection. So there's a data and there's a clock. Clock meaning this is also a synchronous, like SPI, it's a synchronous protocol. But each device has the ability to drive either one of these wires. So this makes it a multi-master system. You don't have to assign rules anymore. The master will become whoever wants to initiate a transaction, which is a big advantage over SPI. And then it uses this open drain style, so it has to have these pull-up resistors. Now sometimes you have to, last spring when we were designing the labs for this course, there was confusion over whether we needed to put these resistors on or if they were somehow internal inside the chips. And as it turned out, they were internal, although I think at one point we had added these pull-up resistors to our breadboards when we did the I2C lab. But somewhere you need to have these pull-up resistors on these 2 wires. So basically, if 2 devices, this is a quiz question or exam question. If 2 devices are attached to an open drain bus, what is the logic value of the bus if one device sends a 1 and the other sends a 0? And of course, it would be a 0 because 1 means that you're not doing anything in terms of the driver. Okay, so let's talk about I2C as a comparison with SPI. So as I mentioned, I2C is a synchronous protocol, meaning that it has a clock that's embedded inside of the wires that make up the channel. But unlike SPI, I2C is multi-master, which is great because you don't have to, you can have anyone can talk. They just have to claim mastership. Or when I say talk, I mean initiate a transaction. It only requires 2 wires instead of 4 for SPI, so that's great. It includes an acknowledgement mechanism that allows the sender to know if the other end of the channel received the message. And the nice thing about this is that it's not even for the whole transaction. The acknowledgement actually has a granularity that's smaller than the transaction. So when you do a transaction, you have to send an address and data, word. And it turns out that in I2C, both parts of the transaction, the address and the data, are both independently acknowledged, which is really cool. So like, it's not even like you could have you know, one part of the transaction might work, another part, you know, may not. Unfortunately, unlike UART that has a parity bit, I2C doesn't have any protocol support for detecting errors. This would be so if there's a, you know, if the receiver were to not acknowledge, it would mean that, you know, either it didn't get the message at all and didn't even realize it was being talked to, or it got the message but it was garbled somehow and there was some electrical noise or something that caused you know, there was some analog mechanism that indicated that there was a transmission error. But anyway, there's an acknowledgement. Also, I2C has standardized bit ordering, so no more having to worry about what the bit ordering is for specific devices. It always uses most significant bit to least significant bit ordering, which is pretty cool. It doesn't have any predefined settings like CPUL and CFA and the parity bit and the number of stop bits. That's to me, that's probably that's a big deal. Although there is a speed mode that you have to worry about. They have different, you know, speed modes. All transfers use program IO behavior. So unlike SPI, which basically had to be hacked in order to get programmed IO behavior, loads and stores, I2C has it, you know, built in. In fact, I2C, you know, you have to do programmed IO type transmissions, and it even allows for stalls during transmission. So, for example, like you know, with SPI, you had these bit times, and you had to, you know, once you started a transaction, you had to be able to provide a bit during each bit period. Whereas with I2C, there's this thing called clock stretching, where you can actually drag out clock periods and actually implement like a stall mechanism, which is kind of neat. But the main disadvantage relative to SPI is that it's half duplex, so only one bit can be sent at a time, and so, you know, it's essentially unidirectional during a transmission. Although, you know, once the master sends something, the slave can respond and send bits the other way, but they can't simultaneously talk, which is okay though, because as I mentioned with SPI, typically you only use SPI in that mode anyway. Like as I mentioned, like usually one half of the SPI channel is idle anyway when you do a load store, you know, a programmed IO transaction. So as I mentioned again, the bits always go from most significant to least significant. So when you read the timing diagram, you're reading it from left to right. Keep in mind though that this is the opposite of UART. So as a, you know, comparing back to UART was least significant to most significant, which is you know, can be confusing. So I mentioned that whoever initiates the transaction is considered the master and acts as the master in that protocol role, but only for that transaction. The receiver is the slave, and so this is one thing though that's kind of confusing about I2C though. So I mentioned, you know, when in talking about SPI is all about edges, clock edges. So when I talked about CPUL and CFA, that the whole purpose of CPUL and CFA was figuring out what edge of the clock to read the data on. And when you write your code in Lab 1, it's all about the clock edge. I2C is actually not an edge sensitive technology. It is level sensitive. And what that means is that bits are conveyed not on the clock edge, but during the time the clock is high. So it's kind of a gating mechanism. So whenever the clock is high, that's when the bits are being sampled during the entire time the clock is high. Now that seem a little backwards because most things are edge sensitive when it comes to timing. But there's a reason for that. It's actually it has to do with the way that signals are sent. So I'll come back to that in just a minute. But basically, the rule is, this is the rule to keep in mind, is that the data. Now, also one other thing too, SDA and SCL are the names of the signals. I think that stands for serial data and serial clock, which I don't like that because I don't see data when I see SDA, and clock should have a K in it, right? And data should have a T in it, to me at least. I always have to think when I look at these SDA and STL to try to figure out what the heck they are. But that's what those stand for: serial data, serial clock. Now, serial data, during a transaction when bits are being conveyed, bits, okay, as opposed to control signals. This is the part that's, I think, is a little tough to get to understand when you're first learning it. The data is expected to change only, when I say change, I mean, go low to high, high to low. The data wire should only change when the clock is low. And so this, think of it, this is the level sensitive thing. When clock is high, the bits are being sampled on the other end of the connection. So you have to be careful not to change data when the clock is high. You have to think of it like a gate. You open the gate, clock goes high, and then you need to stabilize data during the time which the clock is high. Okay, so keep that in mind, that data is only supposed to change when the clock is low, because if that's not the case, then it signals a control operation. And I'll get to that. I'll come back to that in just a bit. So the slave, as I mentioned, has an acknowledgement mechanism where it could acknowledge the address bits. And then there's also a separate acknowledge for the data. Now, the way the acknowledgement works, it's kind of a dance that you have to do, because when you first start the transaction, the master has control over the data and the clock. And in fact, the master retains control over the clock the entire time. But the data line changes hands depending on what phase of the transaction you're in. So what happens is that and this is, again, because there's an open drain. Because these signals are open drain, it means that anyone can drive these lines, and you can use them as inputs and outputs. So what happens is the way the acknowledgement works is that the master is driving the clock, and it sends the address over the data, and after the 8th bit that it sends, it surrenders control of the data bit, the data wire. It lets go. It lets go of it, but it doesn't let go of the clock. So then it pulses the clock, and during that 9th bit, when it pulses the clock, it expects the slave to take control of the data line suddenly, and that during that slot is when the acknowledgement bit is passed back from the slave back to the master. So, and then if the master is doing a write operation, then the master has to immediately take control again of the data line so it can send the data to the slave. So what ends up happening is the master sends 8 bits on data, gives up control of data. The slave sends a bit back on data, same wire, and then the master will then send 8 more bits on data, which is the data it wants to write. Again, this is if it's a write operation. And then the slave would take it over again and send an acknowledgement back of the data, right? Now, on the other hand, it gets more complicated for a read, because if I'm doing a read, the master would send 8 bits, give up data for the 9th bit, and then continue giving up data for the 8 bits after that. So the slave would then send 9 total bits back to the master, which includes the acknowledgement from the address and the data from the 2nd byte, and then the master would acknowledge that it received the data from the slave by taking control of the SDA again. So now you've got this thing where there's basically 4 changes of hands. There's 4 times when the data line switches it's the entity which is controlling it. But the good news is that the master is controlling the clock throughout this whole process. So you don't have to worry about surrendering control of the clock. You just have to worry about surrendering data back and forth, the data line. So I know that sounds kind of confusing, and it is. That's why, as Charles noted there, that the I²C is more complex than SPI because of all this changing hands. But the advantage of it, of course, is that there's only 2 total bits that are needed, two wires, so it's very efficient in that sense. Okay, so now the last thing I want to mention before I get into some figures here is that I mentioned that the data is supposed to change state if it's going to change. Obviously, if you send 2 consecutive bits, then it doesn't, 2 consecutive zeros, 2 consecutive ones, the data doesn't change at all. But the data, if the data changes during the conveyance of an address or an acknowledge or a data byte, the data is supposed to change when the clock is low. However, if the data changes when the clock is high, that will signal a start or stop bit. That's what starts or stops the transaction. So that's considered a control signal. Now, when you read information on I²C, they often will refer to those as start and stop bits, which obviously they stole from UART. You know, UART has a start and stop bit. But in the case of UART, the start and stop bits are actually slots that are slotted for an actual bit that's sent across the wire. Whereas in I²C, they're not really bits. They're more like signals. It's not really necessarily a bit. It's a certain combination of things happening that indicate a start or stop. So it's a little confusing. Yeah, Charles says there's start or stop conditions or state. It's a little confusing to indicate the start and stop bits because, like I said, don't think of them as bits. They're really sort of signals. I like to think of them as signal. Okay, so now let's talk a little bit about the bit ordering here. So one of the issues with I²C is because it's a multi-master channel, there has to be a way to arbitrate the channel. Like when do I get to take control? When do I get to take mastership of the I²C channel? And who controls that? That's a problem. Some buses have an external arbiter that you talk to the arbiter and ask for permission for mastership. And then other types of channels like Ethernet, for instance, is a collision detection system where it's just free for all. And if two entities try to get mastership at the same time, then you got to realize that and back off. Kind of like in a room, 2 people start to talk at the same time and they both kind of stop and someone has to start. So it's self-arbitrating basically. So any device can start a transaction when the bus is inactive. Now, what does inactive mean? Well, as I mentioned, it's an open drain bus. So inactive means it's high. It means there's a 1. There's a 1 on the bus. So, but also inactive means that the presumption is that everyone that's on the I²C bus is monitoring it, is snooping it, and is kind of aware of theirs. If it's not that simple that you're not just looking at the bus and saying, oh, it's 1, that means there's no one doing anything, because of course the bus may be 1 during a transaction. So the presumption is that all the chips that are on the bus are paying attention and are keeping track of whether or not there's an active transmission going on, and if there's not, then there should be a 1 on the bus, at which point it's fair game to start one. But if 2 devices happen to try to initiate a transaction at the exact same time, they need to be able to detect that. And how that exactly works, I don't even know. But there's got to be a way to detect when 2 devices try to start a transaction at the same time. And so when a transaction starts, I mentioned that there's a start bit, and then there are typically 7 address bits that come through, and then there's a read or write flag, and then there's an acknowledge. So now there are variants. I²C is a lot more complex than you might think, and there's actually different ways to do this. There are variants of this where you can use a 10-bit address as well. So the protocol is fairly there's a lot of variants of it, but in this class I'm going to try to just stick to the basic form of I²C. So we're just going to assume there's a 7-bit address, and then there's a 1-bit read or write. So basically the address is 7 bits. The read or write is 1. So altogether, you've got 8 bits. And then there's the acknowledgement. So each phase of this is actually 9 bits. There's the 7-bit address and then the read or write flag. Now, I mentioned that with SPI, typically the read or write flag came first before the address. But again, I also mentioned that that's really just up to the individual vendor, right? But in I2C, the read or write flag is always supposed to be on the right-hand side of the address after the address. So the fact that the read write flag is there is part of the protocol, or at least some variant of the protocol. Whereas in SPI, it's kind of arbitrary where that flag goes. And I know I think I'm maybe getting too into the weeds on this, but just don't be confused, because in this class we'll probably put the read write flag first with SPI and last with I2C. So anyway, so you've got the start, the address, the read write flag, and then someone's going to, the data bus is surrendered, and the other guy takes over and does the acknowledgement bit, and then you potentially switch back depending on if it's a read or write. You do your data, 8 bits of data, and then the acknowledgement, and then your stop condition, your stop signal. Okay, so that's basically how it works. Now, when I first was writing up these slides, I actually had a little bullet point here against I2C saying that, well, unlike SPI, you can't do streaming data with I2C. You can't do multiple byte transactions. But then I looked it up and I realized that actually you can. There are ways that you can actually do more than 1 byte in I2C. And in fact, as I mentioned, it's pretty complex, and there are ways that you don't necessarily just do 1 byte, as I'm indicating here. Well, actually, I have a ... here, so that could mean more than 1 byte sort of follow. But in this class, we'll pretty much just stick to the single byte I2C transaction, because once you understand that, it's obviously not too hard to know how to extend it. So anyway, 1 transaction, some of this is repetitive. So 9 bits and then 9 bits. 9 bits, so you got the address, read write flag, acknowledge, then you've got the data and the acknowledge. As I mentioned, the master always controls the clock. So if you're doing a write, the master controls the data for 8 cycles of the address phase and 8 cycles of the data phase. And then the 9th bit of both would be the acknowledgement, and that would be the slave. If you're doing a read operation, though, the master controls the data for the first 8 bits or 8 cycles of the address phase, and then the slave would control the 8 cycles of the data phase. But again, the master is the one dictating the speed because he's toggling the clock. And then, of course, the master would still acknowledge the data coming back from the slave, and the slave would acknowledge the address coming from the master. So, so you still have you always have to change hands. Every time you do the acknowledge, you have to surrender your SDA, and let the other side control it. Okay, so now let's talk about the start and the stop, because this, to be honest, this confused the heck out of me. Always did. Okay, so here's a timing diagram that we got from somewhere. So what's happening here is you've got SDA and SCL, and the SCL and the SDA, like I mentioned, both of them are open drain, so they're both going to be high normally. They're going to be a 1 if the bus is idle. Now, if somebody takes SDA and pulls it down to ground, that indicates something exceptional, because I think actually we might have got this timing diagram from the 328P manual. If you pull down the data when the clock is high, that's an exceptional condition, because you're not ever supposed to change. I mean, under normal data circumstances, you're not supposed to change the data when the clock is high. But that's exactly what you do to signal a start condition. So, you got both of these signals are just chilling, they're both high. You pull down the data, and that's going to get the attention. That's going to get attention of everyone on that bus, because you're changing the data when the clock is high, and that's why it's remarkable. Okay, then once the once that happens, then the master, assuming that that it was successful, you were able to claim the bus, it's going to send the 7-bit address, the 1-bit read-write, and the 1-bit read-write indicator. Now, if you have multiple slaves listening in, the presumption here is that the slaves each have their own address ranges, and so the slave will know who's being spoken to based on that address. So in order for the address to come across, the master will then set an address bit and then pulse the clock up, down. So up, down without changing the address, right? The address bit. Then it will change the address bit and then up, down. Change the address bit, up, down, right? So you notice that the transitions of SDA are always in between the falling and rising edge of the clock, because you don't want to mess with its data when the clock is high, because when the clock is high, you want to keep the data stable, because it's an edge, it's a level sensitive system. Okay, then after that, you're hoping to get an acknowledgement. Now, another reason I mentioned earlier, the reasons why you wouldn't get an acknowledgement. The acknowledgement is pretty cool, because basically in order to acknowledge, you have to, whoever is acknowledging pulls it low, which is kind of neat, because when you think about it, if I was trying to send a message to a slave that was powered down, for instance, it wouldn't be able to acknowledge by definition, because it would, the default state of the bus is high, right? So when the master pulses its clock during the 9th cycle, it would know pretty definitively that there's an acknowledge, because someone would have had to go through the trouble of pulling that data down, because if no one does anything, then of course it will be high, and that's treated as a NAC, a not acknowledge. Okay, so so then that's the first phase, and then the second phase proceeds like the first. The difference being that the data line is going to be controlled at this point by whoever needs to send data. So on a write, the master sends data. On a read, the slave sends data. And so if this is if this was a read operation, then the slave would just keep control of the data line and then send its bits, at which point the master would take control again during the acknowledgement phase of the data. But if it's a write, then the master would take control again of the data line and send things back. So that's pretty much how it works. Now then you get to the stop condition. So how do you stop? Well, again, the idea is changing the data when the clock is high. Well, at this point the clock is low, so you would change the clock first, set the clock high, and then change the data. So it's kind of the opposite of what does the start. So you basically get yourself into a situation where you can change the data when the clock is high, which is, like, again, it's like an exceptional condition. And so, but of course the ordering happens in the opposite order, because when you started, the clock was already high and you dropped the data, whereas in the stop case, the clock is assumed to be low, so you have to raise the clock first and then raise the data up. So I understand that's a little weird, because again, it's not a bit, it's not a stop bit like you have in UART. It's more of a situation that arises, almost like like it's a sequence of events that have to happen. The clock goes high, then the data goes high. That's the stop. It's not necessarily a bit, and so that's basically it. Now, as you might imagine, I had a heck of a time doing these timing diagrams, because again, it's level sensitive. So and I had to be, it took me a while to figure out how to get these things right with the weird protocol. But basically, you can see that in this case, the data, again, the data changes when clock is high. That's your start. And of course, the stop, if you go to the other side, is when you bring the clock up and change the data. So that's the stop. So I think that's right. And then in terms of reading the bits now, the bits are actually a little easier to read in this timing diagram because you're not looking for edges now. You're just looking for the whole high period of the clock. So basically, you can draw, you can fill in the bits here. You can fill in the bits just kind of when the clock is high. Like you can almost write them inside the little clock pulse, which is kind of neat, I think. So so the address comes in. So master 1 is a 1-bit sent by the master 11111011, and then the read write flag would be a master 0. That's sorry, that should be a 0, right? Yeah, because the data is low. Master 0 there. Sorry, it's typo. And then the acknowledgement would come next. And so we're still looking at the same wire data, but now it's coming from the slave, and that would be a 0. And that's good because it should be 0. That's a positive acknowledgement. And then who takes over? Well, that depends on the read write. Well, what was the read write? It was a 0, which means I'm writing. So that means that the master's in control at this point. Which is why I have M here. So 00110001. So I write a 1, and then the slave takes over, and in this case, the slave is acknowledging with a 1, right? Sorry, with 0, meaning acknowledge as opposed to not acknowledge. And then we have the stop, and the stop and the start, by the way, are both master driven. And again, the stop is clock goes high, so get me into a situation where I can change the data when the clock is high, and then change the data, and that should get the attention of anyone on that bus. And here's another example where I forgot to superscript the 2. Yeah, sorry. Yes, Charles, thank you. The bar means active low. All right. So here's a test question. What is the stop condition of I squared C? It should be a superscript. Not that you can do that in Moodle. Oh, no, you can actually in HTML. Okay, rising edge. See, I already forgot. Rising edge when the clock is 1, right? Rising edge? Yeah, rising edge when the clock is 1. There you go. Stop. These are tough, I think. So yes, that's the answer. Okay, so that's it. That's a good place to stop. Obviously, that's I squared C. Now I'm going to talk next time. I'm going to talk about JTAG and I squared S and CAN. There's other protocols. One thing you'll notice, though, is that a lot of these protocols are actually derivatives of either I squared C or SPI. Like I squared S is for audio and CAN is for automotive control. I think they're both based on I squared C. There's another protocol, a newer one. I can't remember the name, but it's kind of a hybrid between the two. But there's a lot of protocols out there. We're just showing you these because they are, they represent different styles of protocol, but there's a whole lot of them. But hopefully, once you understand these, you can read about any other similar type of protocol and figure it out. And again, these are serialized chip-to-chip protocols. If you were to look at like an on-chip protocol like AXI, it would be radically different. Like in those chip-to-chip protocols, they have explicit arbitration, and they're parallel instead of serial, and they have all kinds of messaging that you can send in, and the transactions between address and data are explicit, that kind of stuff. So, but I hopefully these will be a good give you a good idea of how these chip-to-chip protocols work. And essentially, if you have a kind of an Arduino style system, an Internet of Things or cyber physical system, pretty much everything uses protocols like this from chip to chip. Okay, great. Well, that worked out great. Timing worked out perfectly. If anyone has any questions, go ahead and record them or post them on the chat. I'll just remind you again, we have The quiz is due today. I'll have another quiz out for you on Monday. Programming Project 1 is due on Friday. If you have any questions about that, let us know. You can post on the forums. Hopefully we have a forum open for that. I got to double check that. There should be a forum on Dropbox for the project. And you can also email us. If you do email us, it's best to email all three of us, because that way you'll get an answer. Typically, the way that works is when we get an email, whoever sees it first will respond. And if you post on the forums, that's also good because everyone in the whole class gets that email, which is nice because we typically set up for auto subscribe. So you can opt out of it if you don't want to get all the emails, but that way everyone can see all the questions. So okay, well that sounds good. I'm out of time. I will see you guys on Monday. Thank you.